Now, after looking at all those qualitative description of the kinetic theory model of the gas, finally we come to the math of the gas, which is very complicated, but then I have summarized all the useful formula for you. This is for the whole chapter, starting from 5.1 until the end. And this is one page, a little bit complicated, but then as long as you recite all this, then it will be okay. And in fact, you don't need to recite much. For those you need to recite, I'm going to highlight it in a purple color. And others, I think, in fact, you really need to know how to derive it based on those formula that you have to recite. Now then, let's start with the formula in 5.1. The first one is about pressure in macroscopic view. In fact, pressure is calculated by the normal force over the area of pressing. Next, the general gas law. In fact, you have recited it already, and we have used it a lot of times and practiced for this already. And the good news is, this is given in the DSE formula sheet so that you can directly find this and copy. Next, I have some amendments here. I cross out the other form. In fact, this is just some derive of it, and we don't talk about K here. So that this is out of the syllabus. And same here, Avogadro constant, you know it. Especially if you're studying chemistry, you must be real good. And R is equal to 8.31 as usual. And we cross out the K. This is just another constant for the combination of R and the Avogadro constant. If you're interested, in fact, you may understand it, not very difficult. And next, this is very important because later on we will talk about the proof of the kinetic theory equation, and you need to understand what is the meaning of mean square speed. Here we have the word mean. Mean is having the symbol of a horizontal bar here, meaning mean. Then mean square speed means mean of the square of the speed of the molecules. Okay, so that you can see this is the mean, the bar of c square. C is the speed of the molecule, so that c square is the square speed, and with a bar you have mean square speed. But then, in fact, we are not learning math at all, so that we're going to simplify it to be c square. But you have to know that this c square got the meaning of mean square speed, and this is calculated by the mean of all the square. You can see that the mean square speed is calculated by c1 square plus, this should be c1 square plus c2 square plus c3 square plus cn square. And because we got n molecules here, so that's divided by n, you will have the mean of the square of the speed of all the molecules. Hopefully you try to digest this statement. Okay, and we are not going to use it for this bar representation because we try to simplify it. And then next will be the main dish of what you have to recite, and this is new, the kinetic theory equation. Previously we talked about the kinetic theory in qualitative, so that you know the molecules are hitting each other, something like this. In fact, we can represent it by math, which is PV equals to 1/3 nmc square. But then we don't want this bar representation, so that we are going to use this PV equals to 1/3 nmc square. While n is the number of molecules in the gas, total number, mass is mass of one molecules. M is mass of one molecules, and then c square is the mean square speed, and c will be the Wood mean square speed. Later on we will talk about this on the bottom of this table. Alright, so that you have to recite this. And again, the good news is this is again given in DSE formula sheet, so that again you can copy from the formula sheet. And next we have some derive. This is in terms of density, but then I think you don't need to recite this, because as long as you understand that the density is calculated by mass over volume, then you can directly get the density here, and then without the V, because you put V to the other side, and Nm become mass of the gas, so that the density can come out with m over v. A very simple derive, so that I think you don't need to recite. Next, you have to recite the average kinetic energy of one gas molecule only, with the symbol average Ke. Then the very basic definition will be the average Ke will be half mv squared as usual, and we know c is the Wood mean square speed, or c squared is the mean square speed, so that the average Ke will be using the mean square speed to calculate the average Ke. And then this is not given, so that you really have to recite, but then you know this already, in fact. Next, by this definition, and then we have PV equals to 1/3 over NMC squared, and PV equals to nRT here. You don't need this, because we don't need K. This is just nRT. We try to break down n into big N over Na, the total number over Avogadro constant, which is the number of mole. So that this is what you have recited already and given in DSE formula sheet. Then we can derive this relation of average Ke is equals to 3/2 RT over Na, or we can use PV to represent, and we don't need K here. And the good news is, again, this part is given in DSE formula sheet. And based on this average K equals to 3RT over 2Na, you can see that R is a constant, 8.31. Na is also a constant, 6.02 times 10 to the power 23. So that our very important conclusion is that the average Ke of the molecules is in fact directly proportional to T. That means when T increases, the average Ke will increase, and only temperature can affect the average Ke. Any other things, just like how heavy the molecule is, or what is the pressure, what is the volume, doesn't matter. Only temperature can affect the average Ke. And this is super important when you are thinking about MC. Make sure you recite it. Average Ke directly proportional to T. And that is why we explain temperature increases with average Ke, and average Ke increases with temperature, because they directly proportional to each other. And then next one will be total internal energy. In fact, this is very easy, because the average Ke of one molecule is given above already. And when we are talking about the total IE, in fact, this is also equals to the total Ke of the gas, because in ideal gas, there is no intermolecular attractive force, right? That means there is no potential energy. We just have kinetic energy, so that the total internal energy is in fact equals to the total Ke, in which you just need to times N here to get the total internal energy. The average Ke times big N will be the total. And by our very simple relation, in fact, you can further derive it by just simple math. And later on, we will quickly derive it for you. And lastly, this one is important, this one is important, and lastly, this one is important. The Wood mean square speed of gas molecules. We have two types of symbol here. They have exactly the same meaning. CRMS. RMS means Wood mean square. C means speed, so that CRMS is the Wood mean square speed of the gas molecules. Or, because we are not, again, learning about math, so that we try to simplify the symbol by just using C. But then, this C should be in fact referring to C Wood mean square. So that we try to understand what is the meaning of Wood mean square first. Wood mean square means the square root of the mean of the square of the speeds of the molecules. Hopefully you understand. So that we firstly find the mean square speed of all the molecules, which is mentioned above already, and then we try to take a square root of that mean. Then we get the root mean square speed of it, and we are going to have a simplified symbol, simple c, to represent this. But then they are all in fact the same thing, so that you don't need to recite this. Just need to understand. And then based on this c equals to CRMS equals to square root of mean square speed, we take a square for everyone here. Then we will be able to get, in fact, c square is equal to CRMS square, which is the mean square speed. And that is why we say the mean square speed can be represented by c squared directly, because of this. C square means the square of the root mean square speed. Then based on this idea, in fact you don't need to know much. Then you can again, based on PV equals to 1/3 NMC square, that means we have recited. PV equals to nRT, we have recited, and also average KE is half MV square, half MC square equals to 3RT over 2NA. Based on this three, we can derive all this. And this one is really the one that you really have to recite, because this one is not given in DSE. All these three are given. This one is not given, but then you can easily derive it. And this come up with a very important conclusion again. C is in fact directly proportional to the square root of temperature over the mass of one molecules. This is again super important for MC. Please recite this too. And the physical meaning of this will be, if something is hotter, the gas is hotter, then the molecules will move faster, obviously. And if you have a lighter molecules, for example, hydrogen is lighter than oxygen, then the molecules for hydrogen is in fact faster than the oxygen when they are in the same temperature, so that a hotter or lighter molecules will move in general faster. Then that's it for the whole table. We just need to recite those pink stuff, and in fact all those pink stuff is given in DSE. This is also given in DSE, and this is also given in DSE, so that the only thing that you really have to recite will be C is equal to square root of 3RT over NAM. And one more thing here, some of you study chemistry, then you know that in fact NAM got a special term in chemistry called the molar mass, which is the mass of 1 mole of atom in kg. Like in physics, everything is in kg, but then I know that in chem is g, so that make sure you don't mix up. We want kg in physics. Then the math representation will be NAM, because small m is the mass of one molecule, right? Then times the Avogadro constant, we have 1 mole. Then this is the mass of 1 mole of atom in kg. Hopefully you understand this, and if not, try to talk to your chemistry studying neighbor so that they can further explain it a little bit more to you. Okay, and then we are talking about the distribution. In fact, you know it already. Just to tell you that now we know when temperature increases, the average KE increases, right? Then this graph can show you the distribution. When this is at low temperature T1, then you have this graph. And now when you heat up the gas, high temperature, then you will see a shift of the graph. You can see that they shift to the right hand side, and also the peak drop a little bit, because you need to have the same area on the graph representing the total number of molecules to be the same, so that when you shift to the right hand side, the peak have to drop a little bit to keep the same area, so that the average speed will be here, and the average speed for cooler will be here. You can see that it is shifting to the right hand side, which means faster temperature increase. Everyone is faster. Okay, and lastly, I'm going to quickly do the derive for that, and everything is based on the two things that you recite, which is PV equals to nRT. You recite it, and then PV equals to 1/3 nmc squared. Then this is the two things that you have recite, and also given in DSE formula. And firstly, I want to derive the KE for you. The average KE by definition is in fact this one. Okay, you have this in mind. Then by PV equals to 1/3 nmc squared, I want to, just like puzzle, put this 3 to the other side and this n to the other side, because we want half mc squared, right? So that we have 3 PV over n here is equals to mc squared, right? And we want half, so that we just add in half here for both sides. Then we successfully get, therefore, the average KE will be equals to half mc squared equals to 3 PV over 2n. We have successfully derived it, and we also want it to be representing by another form, by PV equals to nRT, so that we also change PV into nRT here, 2n, and you can see that n and n, you can do some simplification. Big N is the total number of molecules, small n is the number of moles, so that they can simplify into 3RT over 2NA. Okay, and this 2 is a constant, RT constant. R and NA is constant, so that we can conclude that the average KE is in fact directly proportional to T. Okay, this is the first derive. And secondly, we further want to have the total IE, which is the total KE. Then we have N times the average KE of one molecule. Then we have half nmc squared. Then we can also represent it in another way, because nmc squared by PV equals to 1/3 of nmc squared, we have 3. I'll change it in this way so that maybe a little bit easier for you to follow. Okay, and this can also be changed to in terms of RT, so that because PV equals to nRT, right? So that it is also equals to 3 nRT. Then we have 3 over 2 PV here, and also 3 over 2 nRT here for the total KE, which is the total IE. Okay, then this is derived. Okay, so that we have the average KE is equal to this. We have decided it, and then we can derive it in this way and get this for average KE, and also average KE is directly proportional to T, and then we also derive it for total KE and IE, which is also half of the total KE. Yeah. And lastly, we try to derive the most important thing, that is the root mean square speed. We have two ways to do it. Either way is quite simple. I'll demonstrate the first one to you. By PV equals to 1/3 nmc squared. You have c squared here, right? So that you just change the subject. Then you can directly get 3 PV over nm, and then take a square root. This is the root mean square speed. Then you can further change it to another form, just like PV is equal to nRT. You change it to nRT, and then have some simplification, because n and big N here can be simplified. then you have square root 3RT over NAM. That means C is directly proportional to square root of T over M, or T over the molar mass will be another option. Okay, and this is what you have to really, again, recite. But then if you don't want to recite, you can easily start with PV equals to 1/3 NMC squared. As long as you see C squared, this can help us to derive. The other way will be, or you can by the KE, that is, the average KE is in fact half MC squared, right? Which is given by DSE, which is 3RT over 2NA given by DSE. Again, you can see C squared here, so that you can have a very simple change of subject. You will directly get cross out the 2, and then 3RT over NAM, and then square root. You may find this to be a little bit more direct, then either way will be okay. I personally prefer the second way because I think it's more direct. But then, in fact, some question may ask you to represent it in form of PE, in terms of PV, alright, here, in terms of PV, so that sometimes this may be a little bit more useful, but they are in fact exactly the same thing, right? So that, again, I repeat, the most important thing to recite must be this one, because the other two are given. But then if you don't recite, you can't be quick to cope with the speed of DSE. That is why I guess you have to know how to derive it at the same time and quickly derive it, right? And lastly, we will quickly talk about the derive of this PV equals to 1/3 NMC squared. But then, this one is in fact, you don't need to know it. But if you understand the situation, then you will know a little bit more and you will feel a little bit more comfortable to use this equation. And in fact, to be honest, the DSE syllabus that this is RC, but you can find some question about this derive easily here. You can find some derive of it. Let's see where it is. Here, the derive. So that sometimes it will be asking some information about the derive. You can see those are A-level question, but then you really don't know if DSE will just give you a passage and then try to give you those questions. So that it's always good to know a little bit more on the edge syllabus. Then we try to understand this together. We will start with the one-dimension case. That means the molecules is moving in a straight line. Okay, so that we have a box here, which all the sides will be L, and the wall got the area of A, and we are talking about A molecules of mass M traveling with velocity v here, and then perpendicularly, because we are talking about one dimension, so that we have to talk about perpendicular, and then they have to rebound directly backward, so that this keep in the same line. And we have mentioned this already, no matter it is ideal gas or real gas, the collision must be elastic, so that it is going to rebound with the same speed, so that v here and negative v here, and we are talking about a straight line. Okay, so that firstly we want to talk about the change in momentum in the collision, then it will be negative 2mu, because you take this direction as positive, obviously. Then next, the change in momentum for the wall will be the opposite, because action-reaction pair. And then this is the key point. After rebounding, then the molecules will rebound on the other end, right? And then it will come back very soon to hit the same point of the wall again here, okay? So that the molecules will be back and collide again after traveling a round trip. Then the time needed to travel is this. the time interval 2L over V, distance over speed is the time. So that after this time it will hit again. Then the process repeat again and again and again. And then we have to calculate the average force because we want to find the average effect of it due to these molecules, one molecules here. Then we know that to calculate the average net force, this is change in momentum over time in our mechanics. Then by this equation, we can have the change in momentum over time. Then we have mv squared over L as the average force for one molecules, But then, in fact, we just talk about this first. So that the time needed will be 2L over V here because of the round trip, and the FT graph is in fact like this. You have some peak here, and sometimes you don't have any force. But then the process is very quick, and we take the average effect so that we take the average force just like what we did in mechanics and find the average force other than the maximum force here. Then based on this, we further calculate the pressure, which is force over area. Then the area is L squared. Then we have the pressure is in fact mv squared over big V, which V is the container volume. Okay. Then we further make it to be the general case because in fact you get a lot of molecules and the molecules are not moving directly in a straight line perpendicular to the wall, right? We have an angle here. So that we try to deal with this angle problem. That is, we deal with the 3D cases. Then what we have to do is resolve into component. Then we resolve it into the U component first, and then the X component first. So that we will be talking about the X component. So that now the change in momentum is changes to having an X here. And then we again talk about the time of heating with 2L over Vx here because we have resolved, so that our pressure is again what we have mentioned already with an X inside. And now we have N molecules in the general case, right? So that we have to times N for this stuff. Now the total pressure is times N of what we have calculated. And we introduce the idea of mean square speed here. This is why we need to talk about the mean square speed. And next, by symmetry, because previously we just resolved the X component, right? In fact, we have X, Y, Z component, so that we have to talk about the other direction. And by symmetry, X, Y, Z will be the same because of the random nature. And then by Pythagoras theorem, because of Pythagoras theorem, you can say this is X, this is Y, then you combine into the let's do it in this way. This is the X and Y. X and Y, for example, you can combine this into the XY, and then we also got Z here, which is 90 degrees towards each other. This is in 3D, so that these two can further combine. This one can, that one can further combine into this one. A little bit difficult to draw, but then you can combine into this one, which is a 3D. This is a cube. And this will be the final combine by using 2 times of Pythagoras theorem. Then we have c squared. The final mean square speed square is equals to x squared plus y squared plus z squared, and the mean value would also follow. And that is why we have this relation. And 1/3 is come from this. This is why you have 1/3 in our calculation based on this. And that is why we have at the end proven that PV equals to 1/3 NMC squared. Okay, then that's it for all the math, and later on you will be using all this math to try to deal with all those exercises coming, and we will check the answer very soon in next video.